Section 1.2 covers propositional logic. We've been working with truth tables in section 1.1, and we've seen that they can be very helpful. But every time we add a new statement, we have to double the number of rows in the table. For example, when we have one statement P, there are 2 rows in the table because P can either be true or false. When we add statement Q, now there are 4 rows in the table representing all the different combinations of true, false values for P and Q. And if we add a third statement R, now there are 8 rows in the table, again representing all the different combinations of true, false values for those 3 statements. And in general, the number of rows in a truth table is going to be equal to 2 to the n power, where n is the number of statements that we're working with. So you can see that these truth tables can get very large very quickly. Propositional logic is a system that will allow us to make logical deductions formally. This system is comprised of derivation rules and proof sequences, which we will organize in a 2-column proof format. Now, you might remember this 2-column proof format from a high school geometry course. So here's an example that you might be familiar with. Given line L is parallel to line M, prove angle 2 is congruent to angle 7. So the 2-column proof format organizes the statements in the left column and the reasons in the right column. And you always start with the statement that's given. Then any statement that follows should follow from a rule or a definition or a theorem from class. So in this example, we're starting with the given, which said line L is parallel to line M. Then we conclude that angle 2 is congruent to angle 6 because we have a rule that says parallel lines have corresponding angles that are congruent. Then we conclude that angle 6 is congruent to angle 7 because we have a rule that says vertical angles are congruent. And finally, we can conclude that angle 2 is congruent to angle 7 by the transitive property. So I'm not going to make you prove geometry proofs like parallel lines and corresponding angles, but I wanted to show you this example so that you could remind yourself what the 2-column proof format looks like and that you've probably seen it in a previous course. Let's complete the truth table for P and Q implies P. So we're going to start off with the statements P and Q, and we know what those truth values look like. Then we'll need a column for P and Q, and a final column for P and Q implies P. So recall that P and Q is only true if both P and Q are true. So that will happen in row 1. And the implication, P and Q is going to act like the if part of the implication, and P is going to act like the then part. So we're looking in row 1 at true implies true, which is a true statement. And the remaining rows, P and Q is false in those rows. And recall that when the if part is false, the implication is vacuously true. So the statement P and Q implies P is always true. And any statement in formal logic that is always true, no matter what the true-false values of the component statements are, is called a tautology. And since P and Q implies P is always true, we can use a special symbol to indicate that. And in general, whenever you see A implies B with this double arrow, that means that the statement A implies B is true in all cases. Similarly, if you see the if and only if arrow with a double bar, that symbol denotes a tautology containing the if and only if connective. So a single arrow would mean that A implies B is true sometimes, but A implies B with a double bar means A implies B is true always. And similarly for the if and only if symbol. Now let's complete a truth table for P and not P. So we're working with statement P. We'll need a column for not P and then a column for P and not P. So not P negates the truth values of P. And is only true if P and not P are both true, but that never happens. So the final column is a column of all false values. And any statement whose truth table contains all false values is called a contradiction. A statement that is neither a tautology nor a contradiction is called a contingency because its truth values would be contingent upon the true-false values of its component statements. So the next step in learning how to write a proof are to learn some rules that we can use in our proof sequence. So the derivation rules are broken down into two types. We have equivalence rules, which describe logical equivalences, and we have inference rules, which describe when a weaker statement can be deduced from a stronger statement. So we'll start off by looking at the equivalence rules. The tautology A if and only if B is another way of saying that A is logically equivalent to B. And an equivalence rule in this form can do three things. One, given A, we can deduce B. That reads the if and only if from left to right. We can also, given B, deduce A. That reads this if and only if statement from right to left. And third, because A is logically equivalent to B, we can substitute statement A for statement B and vice versa. And this is the aspect of the rule that we use most often. Those substitutions come in very handy when we're writing proof sequences. So there are 5 equivalence rules, and you definitely want to write these down. First, we have double negation. That says that P is logically equivalent to not P. Implication is an equivalence rule that says P implies Q is logically equivalent to not P or Q. Now this one is less obvious, but we use it all the time if we want to switch an if-then statement to something involving or. We have De Morgan's laws, and De Morgan's laws allow us to distribute a negative through an and statement or through an or statement. So first, if you see not parentheses P and Q, that is logically equivalent to not P or not Q. So when you distribute that negative, it changes the and symbol to an or symbol. And similarly, not parentheses P or Q is logically equivalent to not P and not Q. We have commutativity with the and symbol and with the or symbol. So P or Q is logically equivalent to Q or P. and P and Q is logically equivalent to Q and P. And finally, we have associativity. If we have P or the quantity Q or R, that is logically equivalent to the quantity P or Q or R. And similarly with the ands, P and parenthesis Q and R is logically equivalent to grouping P and Q and then saying and R. Now let's talk about our inference rules. The tautology if A then B is another way of saying B follows from A. And an inference rule of this form allows us to do only one thing. Given A, we can deduce B. This arrow does not go both directions, so we can only read it from left to right. Given A, deduce B. And we cannot make a substitution with an inference rule because this implication arrow does not mean that A is logically equivalent to B. We would need the arrow to go in both directions. And we have 5 inference rules. The first one is called conjunction. If we have 2 separate statements, P and Q, we can deduce that we have both statements, P and Q. Modus ponens. If we have 2 statements, the statement P and the statement P implies Q, then we can deduce that we have Q. This comes from the fact that the implication P implies Q, if we know that is true, and if we know the if part is true, that must mean that the then part is true. Modus tollens is similar, but we have not Q and the implication P implies Q. In this case, we can deduce not P. This comes from the fact that the contrapositive is always logically equivalent to the original statement. So, like modus ponens, given the implication and P, we can deduce Q. This one's like the contrapositive. Given the implication and not Q, then we can deduce not P. Simplification says that if we have an and statement, P and Q, then we can deduce that we have P, one part of the and. And we also have addition. If we have one statement P, we can deduce that we have P or Q. So with simplification, we're starting off with 2 statements combined with an and saying if we have both, then we have 1. And with addition, we're starting with 1, and we're saying if we have P, then we could have P or something else. So these are the inference rules. Combine those with the equivalence rules, and we'll have everything we need to write a proof sequence. So watch video 2, and we'll start writing some of these proofs.